This is a transmitter design exercise. We're going to be talking about signals and systems that come from instruments for process control. So we have a typical standard pneumatic transmitters, outputs 3 to 15 psig, and standard electrical signals are 4 to 20 milliamps, although you can also have others that are standard like 0 to 10 volts DC and other types of signals. Okay, there's some of the Internet of Things devices, Raspberry Pis, Arduinos. Those are typically 0 to 5 volts DC or 0 to 3.3 volts DC. That's the range of outputs, although you can also have digital sensors as well that output a sequence of ones and zeros that needs to be decoded. And sometimes these transmitters provide a Modbus interface. So we have Ethernet or serial Modbus with TCP/IP, that's Ethernet or serial communication. And for each of these exercises down below, we're going to develop a linear mathematical expression that relates the measured quantity, so it's, for example, flow, pressure, level, temperature, concentration, with the corresponding transmitter analog result from, for example, psi, milliamps, or volts DC. So let's go on to the very first one, and this is going to be pressure. The pressure gauge produces a 20 milliamp signal at an upper pressure of 500 psig and a 4 milliamp signal at a lower pressure of 0 psig. Okay, so 20 milliamp is means that there is 500 psig and 0 milliamp, or sorry, 4 milliamp. We always use 4 instead of 0 so we know when the wire is cut, and that's going to be 0 psig. So first of all, let's just develop a relationship between the two. Now this one, let's just assume it's going to be a linear relationship. So just the equation of a line is going to be, okay, like this, y2 minus y1, x2 minus x1. So we have 2 points, x1, y1, and we also have x2, y2. Okay, those are the 2 points we know, and those might be kind of in this range where we might have the x values here and then the y values here, and we want to be able to figure out what it's going to be at other points along the way. So those are going to be the x's and the y's. So just rearranging this. Okay, again, this is just a linear correlation. That's going to be this is our slope here. I'll just say m. Okay, so m times x minus x1 plus y1. So that is our correlation right there. Let's go ahead and develop this. First of all, I'm just going to go and plug in these 2 points right here. This is going to be our, this is, we have a signal, and then we want to relate that to a pressure. And so we have, for example, the pressure, and this is in psig, is going to be equal to, and then I've got my 500 psig minus 0 psig divided by 20 milliamps divided by 4 milliamps. Okay, there's my gain. And I'm also going to do the pressure. Sorry, this is going to be the current. I'll just put an A there, minus, and then 4 milliamp, plus, and then we'll have our 0 pressure, 0 psig. So there's a correlation that relates milliamps to pressure. If we want to go the other way, we just do it, the pressure, I'll just put this in milliamps here, is going to be equal to, and then we just flip the 2, all over 500 minus 0 psig. Okay, and then we have times pressure in psig minus 0 psig. That's our 0 value. And then add in the 4 milliamp. So if we want to go either from pressure to milliamp or milliamp to pressure, we've got our two linear correlations there. Now, when I talk about the sensor, we're going to be sensing the psig, and we want to come up with the gain, zero, and span of the transmitter. So in the case of this right here is our gain, our Km value. I'm going to, gain is often our K, and then subscript in this case is M for our measurement. And then the zero value is the lowest value that it can measure. And there is our zero right there, 0 psig. If it went from 500 to 100, then our zero would be 100 psig. And then the span of the transmitter is the 500 to 0 to 500. That's our span, or a span of 500 would be the range. Okay, so there is our expression. We have the gain, zero, and span of the transmitter. And then we have a couple questions. What's the signal expected to be at 200 psig? So I'm going to use this correlation right here and come up with, if I plug in 200 right here, 200 psig, then I'm going to have, let me just go ahead and calculate that here. Okay, so that says it's going to be 10.4 milliamps. That's going to be our signal at 200 psig. Okay, there's our very first problem, and we're done with this one. Let's go on to the second one. Here we have a flow rate, and we want to develop the expression for flow to pressure relationship. In this case, it converts gallons per minute into a gauge pressure. And at 250 gallons per, this one, gallon, let's just do gallons per second. Okay, to this, this pressure, and the flow meter is going to return a signal. Okay, so in this case, 250 gallons per second, and that's going to, oh, you know what? Before we go on, let me just cover this one right here. 600 psig, I forgot about that one. There's our upper range. So it depends on the sensor or transmitter. It might report a 20 milliamp, even though it's 600 psig, it's going to saturate and say I can't go any further, or it's going to send a bad signal and say it's out of range. So this one could be 20 milliamps, even though you'd expect it to be higher if the range were higher, but it might also just give a bad signal. So that's the expected for 600 psig. Okay, let's go back to this one, 250 gallons per second. And this one's going to give a 15 psig signal. And then our 0 gallons per second, that's going to give a 3 psig. Okay, let's go ahead and calculate our gain. Our Km value is going to be 15 minus 3 psig divided by 250 minus 0 gallons per second. Okay, there's our 12 divided by 250 psig per gallons per second. There's our gain. Our 0 is going to be 0 gallons per second, and our span of the transmitter is 250 minus 0, or we have a range of 250 gallons per second that we can measure. Okay, let's develop our correlation, our linear correlation here. It's just going to be, this is going to be flow, and this is going to be in psig, is going to be equal to, and then I'm going to put my Km value here. And then I have my flow that's going to be in gallons per second minus the 0 value, which is 0 gallons per second conveniently. And then I'm going to have to add my 3 psig right there. Okay, so what signal we expect at 100 gallons per second? Let's go ahead and just plug that in right here. So that's going to be 100. Let me just go ahead and do this. Right here we have times, okay, and then this is going to be times the 12 divided by 250. There's my gain, plus 3. Okay, so that says we're going to have a 7.8 psig signal that is going to be returned when we are at 100 gallons per second. Okay, so what's the expected signal, okay, with negative 10 gallons per second when we have some reverse flow? So a lot of times flow meters, again, they're not going to work well. I'd expect it would give a bad signal or even be at the lower value of 3 psig. So it kind of depends on the signal. You have to look at the documentation. But in general, it's not going to be accurate. I don't know what a bad signal would be in terms of psig. Maybe it would go to 0. But normally that's reserved for the case when you lose pressure for your transmitter signal. Okay, so that's a pneumatic signal that you're sending. Okay, let's look at the next one, which is our level. We have an ultrasonic level sensor that produces 1 volt DC at 80 centimeters tank level and 5 volts DC at 0 centimeters tank level. Okay, so we have 1 volt DC, 80 centimeters, and 0 volts DC is going to be, that's going to be, let's see, 5 volts. Let me correct that. Okay, 5 volts DC is going to be 0 centimeters. Okay, so a little bit, switched up here, but I'm going to calculate my gain. And just keep these, these straight. It's going to be 5 minus 1. Oh, there you go. 5 minus 1 volts DC divided by 0 minus 80. And that's going to be centimeters. Okay, so these two correspond to each other, and these two do as well. Okay, and that's going to be 4 divided by negative 80. And that's going to be volts DC divided by centimeters. So there's our gain right there. And we have our 0, which is going to be, at the lower one, we have 1 volt DC is going to be our 80 centimeters right there. So we're going to say that our 0 is going to be 80 centimeters, and then our span of the transmitter is 0 to 80 centimeters. So we can measure that whole range. Okay, let's go and put in our relationship here. We have our linear relationship between the two. This is going to be our level in volts DC is going to be equal to the gain, this Km value that we just calculated, times our level, that's going to be in centimeters, minus, and then our 0 value, which is 80 centimeters. And then we add in our lower value here, 1 volt DC. So there's our linear relationship between the two. And what is the expected signal at 30 centimeters? So let's go ahead and just plug this in to this relationship here. And let's see what we come up with. Okay. So I'm going to go ahead and calculate that here. Okay, so that's going to be 3.5 volts DC. That's going to be our expected at 30 centimeters. So we have a linear relationship there between the two. So just a couple other questions here. The voltage signal from the sensor is transmitted to a nearby signal conditioning rack that is 10 meters away. Every time a large motor in the room is used, the reported level in the tank has more random variation or noise. What is one possible cause and a possible remedy? So that just is, you have these voltage signals that are being sent. So in this case, here is my level sensor. Okay, level transmitter. Let me write that a little bit better. Level transmitter. And that's being sent as a signal to a computer. Okay, and it's about 10 meters away. And every time you have a pump in the room that turns on, you get some random fluctuations that are reported on the computer. Okay, so that might be what it's doing. Then after the pump turns on, it might start doing this as the level transmitter. So what might be happening is, these might be tied into the same power supply. And the motor, just by how it draws power, it might be causing this random variation. Also, there's some field effects that are happening there. Voltage is actually very susceptible to noise. So, other devices that are in the room, like lights or other things, motors, and you can get induced signals into the wire just as you have inductive motors or other things operating in the room. So one thing that you could do is you could convert this to a milliamp signal, like a 4 to 20 milliamp, instead of a 10 volt DC or 5 volt DC signal. And so there's some other things you can do as well. Current is less sensitive. You could also twist the wires. Okay, I don't know how to, you have two wires that are together, and then you essentially just twist the ends and wrap them around each other. That makes it a little bit less sensitive to some of those field effects. But there's a couple other remedies. You could, shorten the length of the wire, put it away from the motor, things like that. Okay, so those are just some things to be concerned about with signals being transmitted and random variations being caused by other equipment in the room or other signals. Okay, and here we have temperature. So fluid temperature is measured with a type K thermocouple, and a thermocouple produces a change in voltage because of the junction of two dissimilar metals at the probe tip. And type K thermocouples are probably the most common ones, wide temperature range, negative 270 degrees Celsius to about 1300 degrees Celsius. So wide temperature range, fairly inexpensive and robust. So what I want you to do is just go find some information online for a typical range and temperature and associated voltage signals for a type K thermocouple. So see if you can find that online, for example, from a distributor. And then how can a low voltage signal source be transmitted without becoming corrupted? Kind of like, similar to the last problem, we want to think about how can we transmit, that signal over a wide temperature range. And so search for information on thermocouple signal conditioners and report on the output specification at least one. And then maybe you want to go a little bit higher, like 2000 Kelvin, and what type of thermocouple would be able to measure higher temperatures. Type K thermocouples are typically only able to measure about 1350 or so degrees Celsius or 1500 Kelvin. So I just have some information that I've pulled off here. Here's the millivolt signal that comes from the thermocouple, type K thermocouple, versus temperature. And you can see that if we were to do a linear correlation between the upper and lower, that you're going to have a lot of error there at particular points. So what happens typically with these is you select a temperature range that you'd like to use. So for example, if you want to go from 0 to 400 degrees Celsius, a linear correlation might work well there. And maybe you want to do another one in this region, and then maybe one more kind of in this high temperature region. So you could have multiple linear correlations like we just derived for different regions. But one of the things you notice here is that the signal is only maybe 0 to 20 millivolts. So very, very small on the millivolt side and very susceptible to data corruption from electrical fields or other things that are going on in the same room. So what's typically done is you have things like signal conditioners, where you plug in the thermocouple probes here. Okay, there's your thermocouple. And then this converts it into something like a 4 to 20 milliamp signal that can be sent along, or it digitizes it as well and sends it to a computer via something like Modbus or OPC or other communication protocols. So this is called a signal conditioner, and it's meant to convert the signal before long distance transmission of that signal. So a couple different ways to do it, but commonly it's converted to like a 4 to 20 milliamp. Okay, and then for the high temperature thermocouple, if you didn't want to use that, type K, and we have a little bit of different ones here. Here's type K, and use this unless you have a good reason not to. But if you needed a higher temperature one, you could go with a type R or type S. Now you'll notice platinum, it's going to be much more expensive, and rhodium. And, high cost makes them unsuitable for general purpose use, but if you need it for high temperature, you could use those instead. So here's a typical accuracy as well for those, and the overall range of those different types of thermocouples. Okay, let's go on down to the next one, the very last one. We're going to be talking about concentrations. And you have a gas chromatograph, measures concentration of gas in a fluidized bed polyethylene reactor with reported values for a lot of the common gases that are in that reactor, such as ethylene, ethane, hydrogen, nitrogen, and isopentane. The values are transmitted with Modbus TCP/IP as integers, because only a single register, 16 bits, is available for each signal. So an unsigned integer requires 16 bits and can transmit an integer between 0 and 2 to the 16th minus 1, or about 65,000. So we want to transmit values that are 0 to 100 mole percent, but we only have 16 bits to do that with. So 16 ones and zeros that we can use to transmit those numbers. And we're going to go between 0 and 65,000 without losing 2 significant decimal places. So how can we do this? So if you just transmit the numbers directly as integers, then if you've got concentration of ethylene, let's say it's 35 mole percent, and then just the first pass of this might be to transmit it as 35, okay, as an integer. But let's say you had 35.2% and you wanted to retain that 0.2 right there. If you transmit it as an integer, it's still going to be 35. But one way to do this is to apply a scaling factor beforehand. So for example, if I had 35.25 mole percent and I wanted to be able to transmit that, I might first of all multiply by 100 and transmit that number as 3525, and that's still within the 0 to 65,000 range. And then when I get it to the other side, I would then divide it by 100, and that would put it back into the 35.25. So this is one of the tricks they play, just with only being able to transmit, for example, 16 bits at a time with the these values. Now in this case I use the 32.23, but you can think of it as like not getting rid of that extra decimal. Okay, and you could also, for example, just divide by 65,000, for example, or multiply by, let's see, not 65,000. It looks like 655, if you're going 0 to 100 mole percent. That would give you maybe the most range there of numbers between 0 and 100%. Okay, so another way to remedy this is to, the integer resolution is to use 2 registers or 32 bits. And you can either do that by, sending this as the first one and that as the second one, or just dividing it up into 2 numbers and then re-encoding that when it gets to the other side. Now another one is you could use OLE for process control, OPC, or other protocols to transmit those numbers as well. Okay, so that's it on concentration. So just to give an overview of what we just covered this exercise on transmitter design with several cases here, pressure, flow rate, level, temperature, and concentration. And just the main thing to remember is that 4 to 20 milliamps is very common. For pneumatic signals, it's typically 3 to 15 psig. And for each sensor, you ought to be able to express what the gain, zero, and span of the transmitter is, and also develop an expression for, in many cases, just going to be a linear expression between the actual measurement that you want to, that you're trying to sense, and the signal that it produces. And then when we come back into our, let's say we're designing a process control loop, we're going to use that Km value right here where we convert a set point into a set point. I'll put tilde there. So this might be, a degree Celsius, and that is going to be maybe a milliamp signal. And then we're going to compare that with our measured value, our sensor, and we'll put a Km there for our sensed value. Okay, and this is going to be a temperature in maybe degrees Celsius, the actual temperature. And this is going to be our temperature in milliamps, our sensed signal. And then we're going to compare those two. This might be a milliamp right here. It would come like into a PID controller, and that might be a valve. Okay, PID controller might output a 3 to 15 psig. And then the valve is going to change, and that's going to be a flow. And then here's our process, for example, maybe a heat exchanger that we're trying to control the temperature of. And, this might be in liters per minute, for example, something like that. Okay, so this is just how the signals translate around, and we showed how to calculate that sensor gain.